Pluto is a far-off and stealthy, more humble planet that was once a part of our closed planetary gathering. However, progressive, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Midiaku have brought Pluto back into the spotlight with a stunning disclosure. They proposed that this cold world may be on a crash course with Neptune, but how exactly should this actually work? And what might be the consequences of such a titanic event? Are we seeing a beguiling and estimable peculiarity, or is there something else to this approaching perpetual mishap? Join us as we inspect the probable consequences of a collision between Pluto and Neptune. In the past, the planet that was later reclassified as a dwarf planet continues to be the subject of interest and focus in the vast universe. As shown by ongoing estimates by leading experts, Pluto's orbit is hazardously close to Neptune's. Astrophysicists deGrasse Tyson and Michioku are both raising the alarm about a potential hazardous impact between these two planets, which could pose a huge risk to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is not like that of any other planet in our nearby planetary group. It requires a stunning 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its unusually elliptical shape, meandering widely from the almost round orbits of the major planets. What makes Pluto's orbit even more exceptional is its inclination, which is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is considerably more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital plan. One of the most interesting aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the natural question, why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out due to its steep slope and elliptical shape. The mystery deepened with the realization that Pluto's orbit does cross Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricate nature of celestial space mechanics. The three-body problem involves figuring out how three items, like Pluto, Neptune, and the Sun, move and influence one another through gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. In Pluto's case, this problem shows how its orbit, the gravity of the Sun, and Neptune's orbit all work together in an intricate manner. The terms non-synchronous vibration and orbital precession, along with the VZK oscillation, are important for this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous vibration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is essential in stopping their orbits from merging. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that the moment it is closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an additional layer of defense against collisions in the future. Another important factor is the VZK oscillation present in this circumstance. Named after three researchers, Zell, Kai, and another, who studied how objects move in space, it involves the way three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull influences how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit close to the Sun is so irregular. Despite Pluto's path appearing whimsical, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation demonstrates that, although things in space may seem turbulent and unpredictable, certain patterns and rules keep everything in balance. These factors help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or drift off course. This three-body problem is critical to understanding how these orbits change because of the way space objects pull on each other. Studying. This helps us learn more about Pluto, our local system of planets, and even further worlds and their stars. In the late 1980s, mathematical simulations revealed that despite these stable properties, Pluto's orbit is actually unstable, with minor deviations in starting conditions leading to huge differences over thousands of years. However, these peculiarities in Pluto's orbit have been found to maintain stability over incredibly long time scales. Monitoring this disruption has been crucial. Later, automatic examinations have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto in which for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a significant role in maintaining Pluto's orbit. Saturn also contributes. These studies demonstrate that immense gravity is powerful enough to ensure that Pluto stays on a consistent path for a long time. So perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These peculiarities are essential in maintaining order and stability in space. Without these elements, the solar system as we know it would be a much more chaotic place. Pluto-sized bodies could collide with others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about a possible upcoming collision with Neptune, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Investigating the depths of space often leads us to confront the strange nature of celestial bodies. Additionally, Pluto's orbit is an ideal example of the unpredictability of orbital chaos, a term used to describe the sensitive dependence of a celestial body's orbit on its initial conditions. This is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, space researchers can see how even minor changes can greatly affect where Pluto ends up. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. Despite having features like non-synchronous vibration and orbital precession to keep, Pluto's orbit can still be erratic and unpredictable. If you start with even a slight variation in the location Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. But even with this chaos, Pluto's orbit remains stable over very long periods. This basically took billions of years, like that means that Pluto's journey around the Sun has a sort of order to it, even though it seems violent at first. Predicting celestial events, especially when they involve erratic orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future paths of celestial bodies, additionally, they emphasize the limitations of our predictive abilities. These models depend heavily on the accuracy of initial conditions, and any small mistake or distortion can lead to vastly different results, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets orbiting Pluto provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and other bodies' trajectories within the framework. So why do they lead? Astrophysicists recently raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event. Neil deGrasse Tyson, a prominent astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful perspectives on the evolving nature of celestial mechanics and the public's interest in the neglected realms of space. Tyson's position on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment, but as an important adjustment in alignment with our growing understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He views the complexities of orbits, like Pluto's, as a sign of how much there is still to discover in space. The fascination with these questions keeps space exploration so fascinating. However, despite Tyson's confidence, his thoughts on Pluto's potential impact with Neptune lay out a different picture. His concerns about the future of Pluto's orbits suggest that there might still be some more secrets to determine whether Pluto will collide with Neptune, or is this just another moment of confusion in the constantly changing universe of space? Only time and further results of our current investigation will reveal. Left with a deeper curiosity about how little we still know about our own solar system, we keep studying these celestial phenomena with the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe in which we exist. The potential for a collision between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges traditional comprehensions of the stability of the planet. The notion that two celestial bodies with such incomprehensibly different properties could collide is both unsettling and intriguing, especially considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, the first thing to think about is the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements with a deep, dense atmosphere. A collision between such disparate bodies would drastically affect their structure and behavior, possibly making an event obvious across vast distances. What makes these speculative effects in particular captivating is the influence of other planets and objects in our solar system. While Neptune's gravity plays a dominant role in maintaining the stability of Pluto's orbit, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key element. Jupiter's enormous mass, powerful gravitational field, and pull provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune.